Hello everyone, let's analyze. So before we get started with today's lecture, let's define a relative maximum and a relative minimum, which you may have heard before referred to as a local maximum or a local minimum. So x naught in the domain of f is a relative maximum if it's the maximum of some neighborhood of x naught. And x1 in the domain is a relative minimum if it's a minimum in some neighborhood of x1. So what specifically does this mean? It means that there's some delta, right, because every neighborhood contains a delta neighborhood. There's some delta radius around x naught, and for all x in the delta radius of x naught, also in the domain, f of x is less than or equal to f of x naught, the local maximum. So the next theorem we're going to talk about is one that you're probably familiar with, but it's a result where the direction of implication often gets confused. So what does it say? It says, well, if a function is differentiable at a relative extrema point, that is a relative max or a relative min, right? So if you have a relative extrema and you have differentiability, then the derivative at that point is 0. Okay, but it's not true that if the derivative is 0, you necessarily have a relative extrema. You could have, for example, what's called a saddle point. So the condition that the derivative is 0 is sometimes referred to as first order optimality conditions. And it's a necessary condition, but it is not sufficient. For sufficiency, you would need second order optimality conditions, which is statements about the second derivative, but we're not going to get into that now. So again, it's important to note that if you have a relative max or minimum and you have differentiability, then the derivative is 0. So let's give the theorem. Let f map the interval a to b to r, and suppose x naught is in the interior of this interval, and that x naught is a relative maximum or minimum. Then if f is differentiable at x naught, then the derivative there is 0. So let's prove the statement. Let's consider the case where x naught is a relative maximum for f on the open interval a to b. Well, by definition, there is a delta neighborhood of x naught. In other words, the open interval from x naught minus delta to x naught plus delta contained inside of the open interval a to b, for which f of x is less than or equal to f of x naught for all x in the delta neighborhood. So the idea is we are going to create a sequence xn which specifically lies in the delta neighborhood of x naught, but is also to the left of x naught. So that's the idea. All right, so xn, right, are entries in a sequence that are in the delta neighborhood and to the left of x naught, but approach x naught as n goes to infinity. That's the idea. Well, because every xn is in the neighborhood, f of xn is less than f of x naught. So the numerator of f of xn minus f of x naught is not positive, because f of x naught is greater than f of xn so long as xn is in the neighborhood of x naught. And remember, xn is to the left of x naught, meaning xn minus x naught is negative, strictly negative. Now, what we have here is a sequence of secant slopes. And as n goes to infinity, we converge to the tangent slope. And of course that limit exists, right? Remember q of x, right? If q of x is the secant slope function, q of x has a limit at x naught. And if xn is a sequence converging to x naught, then q of xn converges. It specifically converges to f prime of x naught. Now remember that q of xn, this sequence of secant slopes, are all non-negative, right? They're all greater than or equal to 0 because the numerator was non-positive, but the denominator was strictly negative. So because every sequence entry is non-negative, and the sequence converges to f prime of x naught, f prime of x naught is non-negative. It's either greater than 0 or equal to 0. Now, here's the thing. We can also make a sequence of numbers that are inside the delta neighborhood that converges to x naught, but from the right. So they're inside the delta neighborhood of x naught, but they are to the right of x naught. Then our secant slope sequence, that is q of yn, f of yn is less than or equal to f of x naught because yn is in the delta neighborhood and x naught is a relative maximum. So f of yn is less than f of x naught, meaning their difference is not positive. And of course yn minus x naught is positive because yn is to the right of x naught. Therefore q of yn is not positive. It converges to f prime of x naught, which means f prime of x naught is not positive. So f prime of x naught is not positive and it is not negative. If it's not positive and it's not negative, it's 0, which is exactly the result we wanted to prove. Now, one of the important consequences of this result is Rolle's theorem. Now, imagine that you wanted to illustrate Rolle's theorem using interpretive dance. And of course, who doesn't? One way to do that is to dance as if you were walking up a hill and then back down. If you walked up a hill and then back down, at some point you were at the top of the hill and you were no longer walking upward and you weren't yet walking downward. That is, the tangent slope at the top was 0. Before you got to the top, it was positive. After the top, it's negative. Now, coming out of the interpretive dance world and putting it back into the ideas of functions, if the graph of a continuous function touches the x-axis at 2 points, a and b, in other words, f of a is 0 and f of b is 0, then there's some point c in between a and b, that's the top of the hill on the x-axis. Then the tangent there is horizontal. In other words, its slope is 0. All right, so let's state formally Rolle's theorem. Suppose f maps the closed interval a to b to R. It's continuous on a to b and differentiable on a to b. Then if f of a and f of b are both 0, there's some point in the interior of the interval c for which the derivative there is 0. All right, so let's first consider the case where f is identically 0 on the interval. Okay. In other words, f is just 0 on the entire interval. Okay, well that's pretty straightforward because, well, f of a is 0, f of b is 0, and f of x for all x in between a and b is also 0. So if that's the case, f is constant, its derivative is 0, and we can just pick any c from the interior, and we know its derivative there is 0 because its derivative everywhere is 0 if f of x equals 0. So that case is fairly trivial, and now that we've gotten it out the way, we don't have to think about the trivial case. Now, let's suppose f is not identically the zero function, but f of a and f of b are both 0. Now, since f is not 0 everywhere, then there's some value for which it's not 0. That's just what it means to not be 0 everywhere. Now, since the closed interval a to b is compact and f is continuous, then we know that f has a maximum and a minimum for x values in the interval a to b. In other words, there exists some x1 and x2 that are global minimum and maximums on the set a to b. In other words, if x2 is a minimum, then f of x2 is less than or equal to f of x, which is less than or equal to f of x1 for all x in the interval. Now, remember, f is not 0 everywhere, so then x1 or x2, either one of those, has to be in the interior, right? They can't both be the endpoints, right? Maybe they're neither are the endpoints, but they can't both be the endpoints, because if the maximum and minimum were 0, well, then f would be 0, and we're assuming that's not happening here. We already took care of that case. Suppose that the maximum x1 is in the interior. Well, then since x1 is a relative maximum and f is differentiable on the interior, the previous theorem, the one we proved, implies that f prime of x1 is 0. Now, in the case that x2 is in a and b, we obtain from the same argument that f prime of x2 equals 0. Therefore, we've shown that there's at least one point where the derivative is 0. Now, by the way, the first formal proof of Rolle's theorem was given by, in this case, actually, Mr. Rolle, Michel Rolle. That's him there. Actually, I almost wore that to class just the other day, but I thought it was a bit much. Now, Rolle was an early critic of Newton's calculus, claiming that it was not very precise and it was flawed, but he changed his mind. By the way, while he's known for Rolle's theorem, he also wrote an important paper on the Gaussian elimination algorithm, or what's also known as LU factorization, which is still used by computers today to solve matrix equations. Now, we're going to use Rolle's theorem to prove the mean value theorem, which is actually quite important. And in fact, Rolle's theorem is pretty important in a lot of applications. For the validity of L'Hopital's theorem, the fundamental theorem of calculus, the validity of Newton's method, the validity of approximations of functions using Taylor polynomials, all of these use, in some fashion, Rolle's theorem. And in fact, urban legends hold that tollways use timings between toll booths and the mean value theorem to issue speeding tickets. Now, is that true? I don't think so, but I mean, look, how many urban legends do you know that are based on the mean value theorem? So the mean value theorem says, in fact, let's actually put it in terms of velocity. Just let's live in this world of the urban legend for a little bit. The mean value theorem essentially says that your instantaneous velocity at some point matches your average velocity. In other words, if I travel 60 miles in 1 hour, at some point on my trip, I was going 60 miles per hour. In other words, if I take the secant over the entire interval, then the slope of that secant is equal to the slope of a tangent line for some tangent line somewhere in the interior. And that is essentially the mean value theorem. If f maps the closed interval a to b to R, if f is continuous on that closed interval and differentiable on the open interval, then there exists a C in the interior for which the derivative is equal to the secant slope over the entire interval. Now, we know this is true if f of b equals f of a. If f of b equals f of a, the numerator just becomes 0, and we say f prime of c equals 0. So when f of b equals f of a, we have Rolle's theorem. So the mean value theorem is really just a generalization of Rolle's theorem. So how do we use Rolle's theorem to prove this more general mean value theorem? Well, we just take f and we just kind of turn it so that the secant slope becomes a horizontal line. That's what this gx function is. If I define g of x to equal f of x minus the secant line, by the way, this formula in the bracket, right, that's exactly the formula for a line with slope equal to the secant slope. Right, so if I subtract the secant line from f of x, I get g of x, and then the secant slope of g of x just becomes a horizontal line. Now, since f is continuous on a to b, well, then so is g of x. Right, we know that by applying basic results on the arithmetic of continuous functions. Also, since f is differentiable, then the algebra derivatives, specifically the sum rule, implies that g is also differentiable. Also, as I said, the secant line of g through the points a and b is a horizontal line. In other words, g of a is 0 and g of b is also 0, putting us firmly in the realm of the hypothesis of Rolle's theorem. That means there exists a C for which g prime of c is 0. But since g of x is f of x minus the secant line, we can actually say what 0 is equal to. It's equal to the derivative of f minus the derivative of the secant line. Well, what's the derivative of a line? Well, it's just the slope, and the slope is secant slope. So I get f prime of c minus secant slope is 0. And if f prime of z minus secant slope is 0, then f prime of c equals secant slope, which is exactly the result of the mean value theorem. So, just to drop some history on you, the mean value theorem was first stated in modern form by Cauchy, and there's an extension of it that bears his name, the Cauchy mean value theorem. Lagrange is typically credited with the first published proof of the mean value theorem. So because Lagrange came before Cauchy, you can see Lagrange looking down his nose at Cauchy. What a jerk. In fact, the mean value theorem in the form we proved is often referred to as the Lagrange mean value theorem. Again, another reason why he's looking down his nose at Cauchy. That's all for today.